Yeah. So good evening. Let us start now. Thanks for everybody for attending this embedded Linux development using Yocto session, and good to have a good amount of crowd today on this particular webinar, whatever we are doing on. Okay, so today we will be studying about how exactly we can use an Yocto, and you can assume this is an intro session where we will give a lot of information about how exactly you can use an Yocto. Okay, so just to give an info about ourselves itself, actually we are doing this session as a part of a TrueChip technology, and TrueChip technology is located in three locations, basically in US, India, and Poland. So this true chip technology is, as a company, we are developing some cutting edge embedded solutions that concentrating and as we already stressed upon, we are a team of core expert people who work on firmware development and RTOS, embedded Linux, and we work in multiple domains. And we also have some product of our own, which we are planning to get to the market also. And then we also do a corporate trainings also for upskilling, where we showcase our expertise and we also help the global teams to do their job in the cutting edge embedded applications. So in this line, we have helped out multiple teams in Intel, Samsung, and Micron to empower them to work on the cutting edge subsystems, where we share our expertise with this organization to do their day-to-day job. Okay, so this is about the true chip itself. And then, so coming back to the session today, just before going to the Yocto itself, we would like to introduce you people to embedded Linux, where we get a full information about what is embedded Linux and what is the, whenever we talk about Yocto, what are we doing with respect to Yocto with respect to embedded Linux? That is something what we will try to look at here. If you look at any subsystem, it will have a development PC because most of our development happens in a development PC. And majority of the time when we are working for an embedded Linux, our development PC will also be of type Linux. And in some cases, our development PC can also be of type Windows, but majority of the time it would be Windows, which consists of necessary tools, compilers, and debuggers that will enable me to compile the code and transfer it to the target subsystem and to debug it. All the debugging tools would also reside on my development PC. That is something which I wanted to stress here if you look at it. So now coming to the embedded target, you will have multiple layers associated with it. Normally we will work on an embedded hardware, that's for sure, but it will also be a bootloader, which will try to give a life to your hardware. And then it will also have an OS, which will try to gel between your hardware and provide a necessary environment for your user space. And since we are talking about Yocto, we're talking about a OS with respect to Linux kernel. And the Linux kernel will have a lot of subsystem within it. It could be a task manager, device driver, networking subsystem, file system. So it could have multiple things. And coming back to the user space, you will have necessary application because OS alone is not sufficient. You need to do some end use application in the user space to use all of these resources and to provide some end application. That will reside in the user space and it would consist of multiple application and libraries to assist the application to do their job. Okay, so now we will try to understand later how our Yocto will help you to do all of these things. So whenever I talk about embedded subsystem, I should have a Linux kernel, I should have a bootloader, and then I should have all the user application with necessary libraries packaged for me, along with the device drivers. So all of these things are required in this particular case and scenario. Okay, so that is something which I wanted to stress here. Now, coming back to the compilers, basically the tool chain, because whenever we talk about all this open source packages, whatever I talked previously, you could be Linux kernel, it could be end application, whatever it could be. So we have a lot of things in this specific case and scenario actually. That is one of the main thing which I wanted to mention here. So to do compile all of these parts, we would need a tool chain. So means I would need a compiler to compile it, and most of the times our application will be of type C or C++. That is the main development environment that is used in case of our Linux subsystem. Nowadays we are also coming with the Rust, but at least until this point, most of our application will be of type C and C++. So we need a compiler in this specific case to do this specific operation. Okay, so we need this in this case to do this specific operation. And for that, we take help of a compiler to compile the code. But compiler would need a necessary set of libraries to do the job. Because the reason is we don't write each and every code. We take the help of the library to do majority of the operation. It could be as simple as performing your string operation, or it can be as complex as creating a thread, dealing with synchronization, memory management. For all of those things, we take help of a C++ libraries. And then bin utils will also assist us to do a lot of other operations, like it could be your archiving. Okay, so it could be your linking. For all those utilities, we have bin utils. And then we will have a necessary, because the reason is whenever you do any of the operation, right, you need a lot of kernel address. So that is when you come up with the kernel address, we need a help of the kernel address to link with that. Okay, so that is one of the main thing which I wanted to mention here. And then after that, we also need a help of a debugger to connect to that and to work. So that is something which I wanted to mention in this specific case. For that, we use something called as a cross compilation tool chain. Basically, the collection of all this thing is called as a tool chain. But if you see this, right, there is a certain term called cross compilation. So we will try to understand in the coming slide what exactly this would mean. This is a specific term. We will just try to understand what does it mean. Now, coming back, you have a source code. That source code is at a very high level language. That has to be converted, because when I want to run on my machine, I need everything to be in a form of a machine code, which is in the form of ones and zeros. To convert my high level language to a machine code, I need a help of a compiler, or what we call it as a tool chain, to do this job. But if you are trying to compile on the machine which is meant to run on the same machine, then we use something called as a native tool chain. So for example, if I'm compiling my code on ARM, and if it's supposed to work on the same ARM subsystem, then it's called as a native tool chain, because it is native to that system. So for example, if I compile my code on x86 system, and if I try to run on x86 itself, then we call it as a native tool chain. But there is also one more category which we call it as a cross compiling, which, as the name itself tells, a cross part. Here in this case, wherever you're compiling the code, majority of the time it is not meant to run on that system. So for example, most of us use x86 system for our development, but most of our target system is of type ARM, and nowadays RISC is very popular. So in that case, whenever I try to generate a binary on x86, it's meant to run on ARM. When I try to run the same code on x86, it may not work, because that is not a right fit for that particular architecture. So that kind of a compilation technique, where I try to compile the code on one machine, but it is meant to work on the another architecture, is called as a cross compilation. This is something what we have to keep in mind. So based on this, there are three category of compiler builds. So based on where the compiler is built, where it's being compiled, and where this binary is being run. So based on this three categorization, we can classify the tool chain as native build, cross native build, and a Canadian build. So for example, if I try to compile the build on an X machine, if I build a compiler on an X machine, and if I run on an X machine, if I compile on an X machine, and if I run on the same X machine, it's called as a native build. If I build a compiler on an X machine, and then if I compile it on an X machine, and if I try to run on a Y machine, it is called as a cross build. Or else, if I want to put it in an architectural sense, if I try to build on a toolchain on an x86 system, and if I compile it on an ARMS, if I use it for compilation on an ARM system, and if I run it on the same ARM system, then it is called as a cross-native build. So in case of Canadian build, I try to build a toolchain on, let us assume, on your x86 system, and I run that toolchain, let us assume, on an ARM system. And let us assume that binary is meant to run on target RISC-V. Then it's called as a Canadian cross build, where the architecture is entirely different. So it's compiled on X architecture. It is run on basically you build a toolchain on an X architecture, you compile it on a Y architecture, and you run it on a Z architecture. It's called as a Canadian cross build. Okay, it's called as a Canadian cross build. So for example, the classic example of a native build is on most of our laptops, which is x86 based system. And most of the cases, right, majority of our build system, for example, tomorrow, let us assume that I take a Ubuntu, I download a tool chain for basically your GCC compiler to compile my code, and majority of the tool chain will be built on an high-end server. That is, most of the times it would be x86 at this particular point of time. And majority of time, your build system where the compiler will be of type x86. And if you take your classical laptop, you download the tool chain there, which is built on x86, you compile there and you run there. That's called as a classic example of your laptops. When you come to the cross build, it is nothing but you compile on your x86 and you build on an x86, you compile on x86 and you try to target on. That is called as a cross build. And your Yocto, most of the time your Yocto will fall in this category. Yocto can also build cross-native build. Also, it's possible, but majority of time it will be of type cross build. Basically, you do an Yocto distro generation on x86, but you try to run on different architecture. But coming to the cross-native, for example, let us assume a case of a Raspberry Pi. You generate a toolchain on x86. You deploy it on your Raspberry Pi subsystem, which is an ARM, and you try to run on the same system. That's called as a cross-native build. Coming to the Canadian build, nowadays many of our laptops are of type ARM in nature. So which means I compile my code, generate a tool chain by using an x86 system. I deploy it on my ARM laptop. Let us assume that this code has to run on my RISC-V architecture, because nowadays RISC-V has become very popular, and your laptop is also, most of the times it's of type ARM, because ARM is also become very popular nowadays, which can handle your laptop power. So at this particular point, you build on x86, toolchain on x86, and you deploy it on ARM laptop, and you try to generate a code for RISC-V, which you run and deploy on the RISC-V. So this comes in a category of Canadian build. So why I'm talking all of this thing is, your Yocto has a mechanism to build the toolchain also. It is not that it will use the native subsystem, because it has to build a toolchain for its specific purpose. So Yocto has a capability of building its own toolchain. So that is something which we want to know, and that is the reason we are stressing this particular point, so that you know what exactly it is trying to do here. And then coming to our target. When we come to the target, it will have different parts. As we saw in the previous slides also, we talked about the target subsystem. It will have a bootloader, which will try to give an initial life to your hardware. And then your kernel, which will try to do a full-fledged management of your hardware. And then your root file system. It contains all the entities that is required to run your subsystem. So it could be your initial init programs. It could be all the services, daemons, your modules, all the configuration files, everything will reside on your root file system. And in some cases, your target can also have your native development environment. For example, your Raspberry Pi. But if you look at the most of the time, the deployed product variant of targets, right, will not have a native development environment because it doesn't make sense for it. So the majority of the time, your target will have a bootloader, it will have a kernel, and it will have a full-fledged root file system. Now, if you look at your storage of your device, it will have a bootloader, and it will have some space to store the bootloader parameters. It will have a kernel, and it will have a root file system. In some in some scenarios, right, your kernel can also be part of your root file system. That's always possible. You can have such kind of an architecture also. But I'm talking about a generic architecture where the bootloader is separate, your bootloader param is separate, your kernel is separate, and your root file system is separate. So now, when we consider the Yocto, we want to generate all of these parts. All are different entities. So all of them have to be configured separately, and it has to be generated separately, and it has to be packaged separately, and it has to be released as a proper distro image. So which Yocto is capable of. So we'll try to understand that. So now, as I mentioned, the root file system contains everything most of the times. If you look at the full-fledged root file system, it will also have even the bootloader on the place. So you might be wondering how the bootloader can be part of a rootfs. So normally, right, your bootloader is also split up into multiple stages. Your stage 1 bootloader will always reside on your storage. Basically, it could be your ISPI ROM or I2SP ROM or even your NAND flash. It could NOR flash. It could be anything basically. The first stage bootloader will reside on that, and the second stage part can reside on your rootfs. That is also possible. In many scenarios, this is done. Then after that, your kernel also can be part of your root file system, as I mentioned, and you will have a real-fledged root file system. And as I mentioned, your root file system is always mounted as /. The starting point of the root file system is nothing but your /. And many of you people, since you have worked on Linux, you will get to know what I'm talking about. Now, coming about the root file system, because the reason is whenever I'm working about the root file system, I should be aware what is the minimum thing I want to represent for the root file system. So for that, if you look at here, the minimum thing what I would need is in a root file system is a init program. So init program is the very first program that will be started in a Linux. It is like giving a life to your user space applications. So basically it's setting up your user space. So your init is the first entry point for your user space. So this does a lot of things. There are a lot of scripts available, and even your init program can be variety of types. There is something called as a BC-boss init. There is system v init. Okay, so there are a lot of init program that is available actually. And then after that, the next thing your rootfs should have is your shell program. It's very important because your user space application will interact with the kernel only via the shell environment. The shell is very important. You can have a very simple shell and you can go till the complex shell. For example, you can have simple sh and it can go till the bash. But there are a lot of variety of shell that is available, but you can select which will fit to your purpose. And the daemon, because a lot of things has to run in a background. For example, let us assume that you want to do an SSH, and SSH should be always running in the background so that whenever somebody tries to connect to my system, the connection should be honored. That is very important. So it should be that I should be able to log the messages. So for that, I need some other daemon. So a lot of daemons should be working, and that daemon will reside on your rootfs. And then obviously I would need a shade library, because reason is there are a lot of components which is common across multiple programs. I don't want to embed all of them in the each and every program. To avoid this, what we do is we come up with a concept called shared library, where we have a common code which is shared by all the programs in a common location. So that all the program, instead of making a local copy within themselves, they will share among and they will start working. That is the responsibility of the shared library would be there. Okay, so that is the reason that will be required in this particular case. So the shared library also will be part of your root file system. And there are a lot of configuration that is available, because the reason is whenever you set up a user space, you have to configure a lot of things. For example, let us assume that you have a lot of services running, how that services should work, how it should behave, and how the networking configuration has to be done. So there are a lot of application in the subsystem. You have to end up configuring them. That configuration will reside in this configuration files. That will also be part of your root file system. And then after that, you, for example, everything in case of a Linux works via device files, basically files. And even the driver is also represented by a device files. So each and every device is represented by a device file, and that is associated with the device driver, and that would work. So basically you would need a device nodes to work with. So that is something what will be present as a part of this device node. And then after that, there are a lot of other folders also you need to create to mount your sudo file system like proc and sysfs. And then you will also need a kernel module that is required for that Linux subsystem to work. So all those things is required. Why I'm talking about all those things is because Yocto will enable to build your root file system also. So since it can build, you have to tell whether you need a minimal rootfs or a full-fledged, full-blown rootfs. All those things has to be represented in this particular case. Now, coming to this talks about the flow, sequence of flow, how the system would start. So normally your bootloader will start, because that is the first piece of software that will be activated on your system. So if you take any of an hardware, the first piece of software that will be activated is your bootloader. That bootloader will try to set up the kernel. Means it will set up all the environment that is required to start the kernel. So in this case, it will be about setting up the DTP, because all of your latest Linux kernel needs configuration for starting up the Linux kernel will come by the DTP. So you have to load the DTP and set up all the necessary basically your other basically init ramfs and other things, and then you will start the kernel. And when the kernel comes into the picture, we would pass a parameter telling that where my rootfs is present by using a parameter called root is equal to. So using that, I will start everything, and then I will also pass in one more parameter telling that what should be my init application, which is the first application I have to start. And most of the time, by default, my init application is /bin init. That is something you have to understand. So that will be the first application that will start, as you see in this picture. And then that in turn will start all the other application one after the other. Basically, it will start all the user space services, then it will start the shell and all the other application. That is something which I wanted to stress in this specific case. And then after that, when we come to this next part, why are we learning all of those things? Because the reason is most of the times, right, our work will involve about developing the board from the scratch, which we call it as a BSP, board support packages. We have to develop everything. See, if you see, right, we looked at what bootloader, kernel, tool chain, multiple things. So all of these things I have to package. I have to select, I have to configure them, I have to customize them, I have to compile them, and I have to package them and distribute them to the necessary people. That is called as a BSP work. And most of the people work in this particular line also. And some people work in a system integration, where they try to configure and integrate multiple user space components. And in many cases, some people work on a specific proprietary application where they try to develop their application and they try to integrate with the subsystem. That is also possible. So these are the three areas where we work with. And if it is a normal desktop subsystem, then it is fine. We can work. But most of the times we tend to work with the embedded subsystem where we have to think about how to integrate all of them in the right place with the right order. Okay, so that is when we need a something called as a build system to deal with all of these scenarios. So now once if you look at it, how can we do all of this activity? So for this, you have to generate a proper images. That's for sure. So if you want to generate an image, there are three ways where you can do with it. First thing is you can build everything from scratch. But the advantage here is you have a full flexibility and you will get a lot of things to learn. So there is no limit for the learning. You will get a lot of things to learn. That is fine. But the problem is you will end up with problems at each and every step. And you need to understand so much of details, which is almost humanly impossible. And you have a lot of version problems also. To add this complexity, there are a lot of version problem comes. For example, X version doesn't work with Y version of other component. So like this, there are so much of component. This interdependency will make this thing as an L actually at the end. And you will end up wasting a lot of time. Because nowadays, deploying your product to the market is much required than playing around and learning things. So it's good for all of us to learn new things and learn new, getting some new learning experiences. But at the cost of what? That's the question. Because getting product to the market faster is much important. So keeping that in mind, one more option that is possible is you can use your binary distro that is available already. Like for example, your Red Hat, Ubuntu, Debian, everything. But what is the problem? It is very easy. The advantage is it's very easy and you can extend it the way you want. But the problem is you can never do the customization. So whether you want it or no, don't want it, you have to use everything that comes up with the distro. And there are a lot of unknowns. And if you want to optimize it and customize it for your purpose, right? It's it's not so easy to do that. And then there are a lot of things you have to do, and then it's not available for certain architectures. So most of the embedded architectures, right? Such kind of distros are not available not for all of your systems. So only option that is available is you have to. So building on your own is required, but thing is that you should not build from scratch. Okay, so because the reason is I can't go with the binary distros that is available in standard. Most of the time it doesn't fit into my architecture, but I have to do build from scratch. So for that reason, we go with something called as a building use. There is a generic framework that is already available in the community, which you can use to build the subsystem. So one such thing is your build root and BitBake and an Yocto. So you can use them to build everything from the scratch. So in this, you get an advantage of both the words. Everything is easily available. There is a proper configuration. You can configure. There is a lot of flexibility. You can customize to the greater extent and you can do whatever you want. And it also deals with compilation and you can fit into multiple architecture with great ease. But only problem is it takes a lot of time to build and then you have to know a lot of things to configure it. That is what we'll be learning in the next coming sessions. So this is something what we have to look at in the specific case. So the one thing what we understood from this is building from the build system is very important. So now, once you look at any of the build system, it will have the following things. Because the reason is whenever we talk about building the image, final image for our embedded subsystems, many of the things we try to use the open source components and we will have some in-house components also. And this particular component can come from different sources. And then, so there'll be a necessary configuration to configure those packages the way they want it. And then it will be built. And that it will end up generating a tool chain, kernel image, bootloader image, and the root of his file system image. So all the necessary things that is required to run my target will come as an output. Okay, so now the advantage here is you are building from source, you have a flexibility, you are doing a cross compilation, and then you will also have a necessary configuration to telling what to build and what not to build. That is something what we will do in many of the build system. So now if you look at it, there are two options, at least the two popular options that is available. One is the build root and another one is the Yocto. So build root, if you look at the build root, right, It doesn't provide the great amount of flexibility what Yocto gives, right? That kind of a flexibility you don't get it in this case. And then most of the times your build route will not be able to generate your final deployment image. It will generate all the packages, but not your final deployment image. So you have to do a lot of work there to get the final deployment image, but Yocto can do all of those things, and it has a lot of other things also available. It can offer a lot of other things, which we will discuss later also. Okay, so looking at it, so your Yocto weighs a lot. So that is the reason a lot of people use Yocto as their build subsystem nowadays. But now coming to the Yocto, so Yocto is also an open source collaboration project itself, and is used to create your custom embedded Linux system, and it provides a complete build system framework. And then looking at the organization structure, how does it look like? It is founded by Linux Foundation. It was established in 2020, and it is managed by Richard. And then it's supported by global community of developers. So one of the main capabilities of this is it is cross-platform. It supports cross-platform development. It supports multiple architecture, and it provides multiple build environments. And you can customize that to every level. That's one of the main thing what you can do. And one of the main key features of this, it provides layered-based architecture. So it is fully based on layer-based architecture, and it provides package management. It can generate cross tool chains, and it also takes care of generating documentation also. So we will, this also is one of the capabilities what Yocto can do. So because of this, lot of industries tend to use Yocto as their standard basis. Now, coming to the Yocto itself, based on the whatever we saw in the previous distro, it will does say all the things Yocto provides, but it also provides a mechanism where you can also package your distro the way you want, and you can generate a final rootfs image. That is also possible in case of your Yocto. That is one thing. It's basically what I want to stress here is your Yocto will be able to generate a final distribution. That is something which I wanted to stress here. Now coming to the Yocto, the main base for your Yocto is your BitBake. Okay, so the BitBake is the main base for your Yocto. The BitBake is something like, it's a task scheduler. It's something like your make ultimately. It's something like a make utility. And the BitBake works on a different, ultimately the code is also written in a text file, and it has something called as, you have to write some procedures and requirements to achieve the job. And the BitBake file will be formed. Say, for example, we write a make file, right? By using a name called make file, something like that. You will also have a different convention for a BitBake. It's called BB. You will find many files in your Yocto, which ends with BB. That is nothing but your BitBake files, which is also called as a recipe files. And then you also have another concept called append files, which is called as a .bp append, which will provide an instruction how the build should happen. Same way like a make gives an instruction, right? How the compilation should happen. The same way even this also gives an instruction. And this BitBake can handle multiple dependencies very easily. The build order, dependency, everything, it can be taken care by the BitBake mechanism in place. And it is written fully using the Python. Okay, this mechanism is fully written using Python. And it requires Python 3. This BitBake is fully derived out of Python 3. Yeah, so this is one of the main thing which I wanted to stress here. Now, let us have a small look at our hands-on to see how exactly we can use the BitBake. So as I mentioned the BitBake is a build environment. Let's have a small session to understand how exactly we can use a standalone BitBake to do the job. Okay, so if you want, you can also do everything by using the standard mechanism in place also, without using a Yocto also, because Yocto also ultimately uses the BitBake only. Okay, so we will see how exactly it can be done. So now if you come here, just give me a second. So if you see here, I already have an example here where I've written a simple BitBake code, something like your Yocto code. Sorry, something like a make file. I've written a BitBake code where it has classes, configuration, and necessary code to do the job. So now if you see here, I've created my layer. So in this my layer, I've created some BitBake file. So in this BitBake file, I'm doing BitBake bb.plain is meant to throw some messages. So I'm doing do build, and then it's trying to print some messages. That is what I'm trying to do here. Okay, so now the running is done by I've written a build script to do that. If you see here, just give me a second. So I've written one layer to do it. And then I've done all the necessary configuration that is required for the BitBake is present here. And the BitBake repo itself I've downloaded here to use it. Then after that, if you see this, we have a build. In this case, if you see here, we are using a build.sh to do the build. Actually, if you see here. So this is what will be steps to run using a standalone BitBake. Now, if I run it, if we do this, see here, it found the dependency, it parsed it, same like a make file, it analyzed it, and then after that, it executed my BitBake file. Something like this. So this is one such example to showcase how the BitBake can be used as a standalone. So if you want, if you want to develop anything from the scratch using BitBake also, you can do it. But Yocto also has done something like this in a much complex way to develop its own build system. So what I'm trying to tell is BitBake is the first step for developing an Yocto. That is the main thing which I wanted to stress here. So now coming back to this. So one more thing what you have to know is that recipes. Now we know that BitBake is the base, but the input to the BitBake is a recipe file. Means it's something like a make file for the make. Recipe is for the BitBake. It will contain all the necessary. It tells how to. It gives all the information about building some component. Okay, it tells that what is this component about, and it will have some certain syntax, how to build this recipe, the dependencies, everything will be taken care in the specific case. So if you see this picture, rootfs is the final output what I need. To do this, I need certain recipe called dropbear, libbake script, zlib, png check, and libpng. But if you see here, dropbear as a dependency with zlib. So now, if I want to build a dropbear, I need zlib. So zlib will be the first thing that to be built. And it also has a dependency with libxscript. So libxscript and a zlib is the first recipe to be taken up to build. That is the dependency tree. And similarly, to build png check, I have a dependency with zlib and libpng. Libpng has a dependency with zlib. So this kind of a dependency handling it will do. But dropbear is one such recipe, libcrypt is one such recipe, zlib is one such recipe, and png check is one such recipe, and libpng is one such recipe. That is one thing which I wanted to stress here. Now, coming back to the task, see each recipe inside will tell each and every step how the build process should work like. It's like a breaking down your build process inside your recipe, how the build should happen. So if you look at the task, there can be a lot of tasks that can be associated in the build. For example, fetching means to build that particular recipe, you might have to download certain components. That is called as a fetch task. And once you have fetch, you have to configure it. That comes in a configuration task. And then you have to compile it. That comes in the compilation task. And then at the end, you have to package it. That comes in the packaging task. Okay, so then it's possible that one task will depend on the other task. So for example, if you see here, dropbear needs 2 packages. Okay, it has to fetch 2 packages that it would do. And then after that, it will try to do a configuration. But configuration somehow has a dependency with libcryptx. And that is what has been done in the specific case, if you see here. That kind of an interdependency is also we can create in case of a Yocto. And this mechanism is called as a task in this Yocto. And then after that, you also have a POCO in case of your Yocto, which we call it as a POCI. So POCI is nothing but a Git repository which is nothing but a reference distro. Pokey is a reference distro for your Yocto project. And your Yocto is always uses a reference mechanism called Pokey, which contains a lot of other things like a BitBake, Open Embedded Core, Yocto docs, Meta Yocto, multiple things will be part of this Pokey, or a Git repository. So whenever I want to build anything, I will always try to use the Pokey repo only to start with. And Meta Pokey is one of the meta layer that is present with the Pokey. That is something which you have to understand here. Then after that, if you come back to the metadata, as we saw in the previous case, metadata is nothing but a list of configurations, recipe and classes, everything included. Okay, a lot of collection of all these things is available in a form of a meta layer. And most of the times the meta layer, all this collection can be a meta layer. For example, you can have your TI meta layer and you can have your x86 meta layer. You can have your multiple meta layers that is possible. So it's possible that multiple meta layers are required to perform certain operations. Okay, so for example, if you take a open embedded core, this is about the metadata. Coming back to the layer is very important. All the necessary entity that you want to combine will come in a form of a layer. An open embedded core is one such core layer that is present in Yocto, and it will support multiple architecture if you look at here. So everything is possible, and other than that, this will also support you to use the QEMU emulation. That's one of the main things which I wanted to stress here. Okay, and then if you look at the complete Yocto, it will have following things at a big picture. Most of the things comes from an open embedded core project, where you will have an open embedded core meta layer, and internally it will have a multiple recipes, and that will be part of your Pokey project, where everything will come, and your BitBake is part of your Pokey project. And then after that, you can integrate multiple meta associated with this mechanism. So when you start with the initial project, you will end up using the Pokey, which will contain all of this thing, open embedded plus Yocto related part. And then if you want, you can start integrating multiple meta layers into our project and extend it the way we want. So this is how the full-fledged Yocto would look like actually. And then coming to the setup, since the build takes a lot of time, so what we have done is we have set up everything and we have built. So if you see here, I've already downloaded the Pokey and I've set it up. Okay, so now to run it, normally what we have to do is we have to do source build. So this is the command to source it, and then we have to build the image. So that is called BitBake, which target to build. So I will tell core image. So let me do one thing. So I will do this. So the build will happen. Normally, since I've already built it, will take well less number of time. Otherwise, it depends on the system capabilities, and the build can take any amount of time. But at least on my system, it took like around 3+ hours. I don't know on your system capability, it may take more or it can take less also. Now, this is the things what you see here, and then I've configured it to build for my QEMU machine because I want to use it using a QEMU emulation. So which is an emulation of your x86-64 processor. So we can emulate and see the output. So it means it is emulating the processor. I'm not deploying on any of the target, which we'll do later at later stages. But in this case, I'm deploying on the QEMU machine, which is a machine simulator, and it will show which will simulate your something like a laptop. Now, if once I run this, actually, if you see this and if I run this, if you look at this, so let me run it. Yes, it is starting a QEMU environment. You can see it's starting my image. If you look at this. So if I log in, you can see everything. You can check it out and you can see this. So for example, this also has a networking in place. We can also see how the things are working fine. If you want, we can also debug it, which will show, which we can discuss at a later point of time. But see, it can work both the ways. Everything, the full-fledged system has come up. And this, the image that is required for all this thing to work has been derived and come out of Yocto. That is some things here that in the deployment, there is an image that is generated in the necessary folders, which has come out. Okay, so this is one of the mechanism how we can set up the Yocto itself. That is one of the main thing which I wanted to stress here. So let me go back. Yeah. So now after that, and coming to the final thing. So if you look at it actually, so now we went through the basic of Yocto. In case if you want to learn and understand more about Yocto, we have an Yocto training session that will start from 12th of July, where we will go to the in-depth. Currently, we have just gone to the basic intro to Yocto. We will go multiple levels to greater depth, and then we will explain you how this Yocto subsystem can be used for a full-fledged and to generate a deployment image as per your requirement that can be achieved. So that is something what we are targeting, and that would start on 12th of July. You people can register, and this would be in weekend classes. So since it is a weekend classes, the working and this session is targeted mostly for our working professionals, and most of the times they would be free only on the weekend. So that is what we are targeting on the weekend. So where we will be taking a 4-hour session per week, means 2 hours every week. Every week it could be Saturday and Sunday. That is what we will be targeting. And then after that, one of the unique point about this sessions are we will have an LMS, and we'll have all the training element, training material downloaded to LMS. You can download, you can view, and you can work as you need. And then there'll also be an assignment every week. For example, if we conduct some sessions every week, we'll try to give an assignment so that you can do the assignment, and then we will review it, and then we will check out how the things are working out. And then at the end of the course, we will also have the project which will try to evaluate and make use of your experiences and develop some live mechanism in place. That is what we'll be targeting in this. So it could be 1 or 2 projects. It depends upon the course, how it goes about. We can plan more number of projects. And then after that, at the end, we will also try to give a grade based on your how are you trying to do the project, and a presentation. There'll also be a presentation, and based on that, we will also grade it. And then after that, we will also give a certification of completion to see that you have completed the course. So this is something what we'll be doing, and the entire thing will be targeted for 40 hours. So basically what we are doing is to do all of this thing is 40 hours is what we are targeting for. And if you need any of the information, you can go to this website, what we have stated down, so that you can get all the information. Okay, so that is something which I wanted to mention in this case. Yeah. And by the way, thanks for attending this session. Okay, so now let us wait for any questions. If any, do you have any people have any of the questions, you can please let us know. So any questions? Yeah, so this training course will be for 40 hours, and that is what we are targeting for, and we want to close everything by that. Yeah. And then, well, yeah, right. And if you look at it for one of the questions here, yes, we'll be doing the session on boats. Basically, we are targeting to do this entire course on a BeagleBone. That is what we are targeting for this course. And then we will also try out something on the QMO also. So we will be doing 2 parts here. First thing is we'll be trying with QMO, and then we will move on to the board and we'll work with the board. That is something which I wanted to mention here. Yeah, so it will be targeted for weekends. The timings we can decide based on all the people, and then but it will be targeted for 2 hours, one for Saturday and other one for Sunday. That is something which I wanted to stress here. Yeah. Okay, then. So if you don't have any questions, then we will sign off for the day. And thanks a lot for being such a good audience. And thanks for everybody. Yeah. Okay, then. Fine. Bye. Have a great day.